Stop.
So I will share my screen. Okay. So can you see the screen?
Yes, yes.
Great. So I will start. So good afternoon, everybody. My name is Javier Junquera. I am a professor at the University of Cantabria in Spain, and it will be my pleasure to deliver these lectures in the preschool of ASESMA. So I will be with you during the next 3 weeks, explaining very basic concepts related with quantum mechanics, and in particular with the Schrödinger equation and the solution of the Schrödinger equations for particular cases. So the first lecture today, the goal, as I will explain in a few minutes, is to present all the ingredients that appear here in the Schrödinger equation, and then start an explanation on the most simplified model, that is a one-dimensional model. And then I will explain the separation of variables, and then I will move to the three-dimensional Schrödinger equation, and I will describe a little bit the principles behind this very important equation. Next week will be devoted for the solution of the Schrödinger equation in particular cases. In particular, in the free electron gas that would be relevant in metals, then the hydrogen atom and the harmonic oscillator. And finally, the third Thursday, 3 Thursdays in a row, will be devoted to questions and answers. So if you have any question regarding the talks, then you will have plenty of time to discuss with me. So today, the lecture will be devoted to an introduction to the Schrödinger equation. So here, the first thing that I would like to emphasize is a very important reference that I will follow in this lecture. Indeed, most of the materials has been borrowed from this textbook that is called A Student's Guide to the Schrödinger Equation by Daniel Fleisk. And I extremely recommend the lecture of this book for newcomers in the field, because it's self-explanatory. It's going step by step in a very careful way and in a very...
I'll see what can I thank you.
Hello? Okay, so I extremely recommend to read this reference. So a little bit of history. The Schrödinger equation is almost 100 years old. It was published by Erwin Schrödinger in this paper here that appeared in December 1926. The history tells that Erwin Schrödinger retired to a small house in the mountains in the Alps, and then he was trying to find an equation that describes the behavior of matter as a wave. And then he came up with the Schrödinger equation, with the equation that is named after him, and then solving the equation for very simplified systems, he was able to get the proper properties of the atoms. And then he was very happy, and then the equation was extremely successful. Here you can see the virial place of Erwin Schrödinger and his wife, and then you can see how directly in his virial place his equation is written. So what will be our goal? So this is a preschool of ASESMA. So what is the goal of ASESMA? When you are going to this school, hopefully in Ghana, the things that we are going to describe there, is how to describe the properties of matter from theoretical methods that are firmly rooted in fundamental equations of nature. And by properties of matter, I refer to structural properties. So what are the ground states for a given system, or even some metastable states where the atoms will be localized. We can discuss about electronic properties. So whether a system conducts electricity or not, if we are dealing with a metal, or if we are dealing with a semiconductor or an insulator. So we are going to compute band structures, and then we can check if we have a band gap or not, if the band gap is direct or indirect, and things like this. But we can also discuss about vibrational properties that are very, very important for thermal conductivity, for instance. And then these vibrational properties are related with phonons. And then we will discuss the harmonic approximation and how to compute the phonons from the basic equations of nature. But electrons, besides charge, electrons do have also a spin. And then we can order the spin in different magnetic structure that may be ferromagnetic, antiferromagnetic, ferrimagnetic, altermagnetic. So there are many different magnetic states. And then using this or just solving these equations, we can also find what is the most stable magnetic structure. Or we can describe the interaction of the matter with light. And then we can compute optical properties. So we can check if electrons would be excited or not under the influence of an external electromagnetic field, and then compute this absorption or emission of light from the structures. So those are just a few properties. There are many more, but those are just a few properties that will be affordable just from the methods that will be described in the school. So here I am talking about fundamental equations of nature. So what is the most important fundamental equation at the level of energy that we are dealing with? So we are going to deal with atoms, and we are going to describe solids and molecules from an atomistic point of view. And within the relevant energy scale that we are going to deal with, the most basic equation in nature is the Schrödinger equation, that assuming that we are in a non-relativistic limit, it takes this form here that I will describe step by step in a few minutes from now. So here we have a basic ingredient that is this object that is psi, that is the wave function that in principle depends on all the coordinates of the electrons and all the coordinates of the nuclei, and it may also depend on time. And then we have this other object here that is the Hamiltonian operator. And this Hamiltonian operator is an operator related with the energy of the system. So this Hamiltonian operator will be is made of the sum of the kinetic energy terms plus any potential that is relevant in our problem. So in our problem, the only relevant potential is the Coulomb potential. That is nothing else that the product of the charges of the particles divided by the distance, the interparticle distance here. So essentially, that's the kind of things that we are going to solve. The point is that this Hamiltonian cannot be solved exactly. And there are only, it can be solved analytically only in a few cases. For instance, in the case of the harmonic oscillator, in the case when we have two particles, for instance, in the hydrogen atom or in hydrogenoid atoms, or numerically, we can solve it in an exact way if we have a very few particles. However, there is a complexity wall to solve this problem if we increase the number of particles. And this is due, as Richard Martin explained last week, this is due to the electron-electron interactions. So if we assume that the electrons are interacting between themselves, then the complexity of this equation increases exponentially, and then at some point it will be totally unsolvable from a fundamental point of view. But even there is another practical problem. So even if we can solve it, imagine that we can solve this equation exactly, the practical problem is that we need to solve it for a very large number of electrons. In particular, the number of electrons and nuclei in a very small amount of matter typically is of the order of 10 to the 23. Okay, so this is the Avogadro number. That means that the computational cost increases exponentially with the number of electrons, and it will be totally impossible to solve the Schrödinger equation for such number of particles. So the thing is that we need to solve the Schrödinger equation because in solving the Schrödinger equation, we will have access to all the properties of that I was mentioning before, the structural properties, the optical properties, the magnetic properties, and so on and so forth. But then we have to make some approximations. And this is the main goal of the ASESMA school. Okay, so in the ASESMA school, we are going to teach you about how to solve the Schrödinger equation in a practical way. So the Schrödinger equation, as you have seen, is the most fundamental equation in nature at the level of energy that we are going to deal with, and therefore I think it is very important to understand what is the meaning of the Schrödinger equation. Okay, so that will be the first part of my talk today. Then I will describe the characteristics of the Schrödinger equation. Then I will move about how to derive the time-independent Schrödinger equation in a very simple problem in one dimension. Then I will just generalize this the Schrödinger equation in one dimension to 3 dimensions. And finally, I will describe what is the meaning of the electronic wave function and the principles of the Copenhagen interpretation. So the thing is that, as you have seen, it is very important to solve the Schrödinger equation, to know the properties of a system. And today, what we are going to do is to examine this Schrödinger equation starting in a very peaceful way. So that's the first thing that I will describe here. So here you are the shape of the time-dependent Schrödinger equation in one dimension. So the goal of this lecture today is to present all these ingredients that are here involved in the Schrödinger equation, going step by step. So I'm going to start with a very, very simple problem, just one-dimensional problem. And that's the shape of the Schrödinger equation in a one-dimensional system. So in the time-dependent form, you have here I is the imaginary unit. Then you have here h bar, that is the Planck's constant. Then we have the partial derivative of this object that is called the one-dimensional wave function with respect to time. And this is equal to minus h bar squared divided by twice the mass, multiplied by the second derivative of this object, again, the wave function with respect to the position twice, and then the potential times the wave function. So let's go one by one to this to the ingredients that appear here. So let's start. Let's start with the first ingredient, that is the partial derivative of the wave function with respect to time. In principle, this object here, that will be the solution of the Schrödinger equation, this is the wave, the quantum wave function. In principle, it may depend both on the position and time, okay? X and t. So this partial derivative represents the change of the wave function over time, only over time. So we fix a particular point in a space, we fix X, and we check how this object, this wave function changes with respect to time. So if we fix a given location and then we plot the wave function as a function of time, this object here will be the slope in that graph. So the units in the International System of Units will be 1 over second and the square root of mass. So this is one of the ingredients of this Schrödinger equation. Let's move to the second one, that is the numerical value of the imaginary unit. So this number here is a dimensional, and it represents the square root of -1. So the multiplication by this number here, it has the effect of changing the phase of a complex number by 90 degrees, okay? So if you have a complex number here, you have the imaginary plane where the real component is represented in the x-axis and the imaginary component in the y-axis. So the multiplication by this I just produces, for instance, a movement from the positive real axis to the positive imaginary axis, or from the positive imaginary axis to the negative real axis. So the most important thing here, besides this, the effect of this I, is that it immediately tells us that the solutions of the Schrödinger equation, the quantum wave functions, may be complex. And this is a very important issue that will appear afterwards at the time of describing, for instance, oscillatory waves and oscillatory behaviors of this of the solutions. Okay, and this may be a difference with respect to other equations in classical physics. Then we have another ingredient that is the h bar. H bar is the modified Planck constant, or said in other ways, is the Planck constant divided by 2 pi. So this is a constant that takes this value here in international system of units. And this is the constant of proportionality between the energy and the angular frequency of a wave. Or it's also the constant of proportionality between the momentum and the wave number of a wave, okay? And it is h, the modified Planck constant appears twice in the Schrödinger equation. It appears here at the left-hand side, multiplying the partial derivative of the wave function with respect to time, and it appears linearly. And this is due to the fact that the energy expression is also linear in h bar. But it appears also here at the right-hand side, it appears in this numerator as h bar squared. So the dependence here is quadratic because this term here will be related with the kinetic energy, and the kinetic energy is related with the square of the momentum operator. And the momentum operator depends on h bar, so the square of the momentum operator will depend with h bar squared. So as you see, this h bar appears twice in the Schrödinger equation. Then another ingredient is the mass of the particle or the system associated with the quantum wave function. And the mass here, as in is as a measure of inertia or a resistance to acceleration. And in the International System of Units, it's measured in kilograms. Okay. And finally, we have here another term that is the second derivative of the wave function with respect to the space twice. So here, remember that the first derivative of this object here, of the quantum wave function, with respect to the position, reflects the change of the wave function over space. So this is a partial derivative. Remember that this object here may depend on space and time. So here, what we are doing is just to fix the time to a particular moment, and then check how this object is changing with space. So the first derivative reflects the slope of the wave function plotted against the position. So the second derivative, that is the thing that appears in the Schrödinger equation, is the change in the slope, okay? Or say it in other words, it is the curvature of the wave function. And the units in the International System of Units is 1/meters to the power of 5 halves, okay? And then the last ingredient here is the potential. And the potential, the external potential in principle, may depend also on the position and time, okay? So one important thing in quantum mechanics, as I will describe next week, is that in quantum mechanics, the particle's total energy may be less than the potential energy in some regions. So classically, this behavior is unallowed, Okay, so classically, those regions where the total energy of the system is smaller than the potential energy will be prohibited for a particle. Here in quantum mechanics, there are still solutions that will represent evanescence solutions. Okay, so they will decay exponentially in these regions, but there is a non-zero probability of finding the particle there. On the other hand, if the total energy is larger than the potential energy, then those are the regions that classically are allowed, and we will see how in quantum mechanics we might have oscillatory solutions in those regions. So the energies of the potential are, in the International System of Units, are joules or kilograms per meter square divided by second square. So those are essentially all the ingredients that appear in the Schrödinger equation. Okay, so we have gone one by one explaining the meaning of all of them. So finally, let's just combine all of them together. So we have presented all of them one after the other. So here they combine in the Schrödinger equation, in the one-dimensional Schrödinger equation. In this particular case, time dependent in this way here. And then here we can check how this is a differential equation because it involves the change in the wave function both over time here at the left-hand side and over space here at the right-hand side. It is partial because the wave function depends both on space and time. So this differential equation involves the partial derivative with respect to time or the partial derivative of the wave function with respect to space. In this particular case, this is the second derivative. So this is a second order differential equation because the highest order in the equations is a second derivative, and it is parabolic in the sense that here this partial derivative is linear, this partial derivative here is quadratic, so this resembles or is analogous to the combination of the first order algebraic term and second order algebraic term in a parabola. So in a parabola, you have that y is equal to a constant x squared. So you have something similar here. Okay. So those are the characteristics of the Schrödinger equation. And then we can get also some flavor of its meaning if we compare this quantum equation, the Schrödinger equation in quantum mechanics, with some equations that appear also in classical mechanics. So let's take a look, for instance, to this diffusion equation in classical mechanics, where you have a given property, maybe temperature or density of particles or whatever, and this property depends both on space and time, and then the diffusion equation in classical mechanics takes this form here. And as you see, we have here at the left-hand side, we have the partial derivative of, let's say, temperature with respect to time, and this is equal to a constant times the second derivative of this function with respect to space twice. We can rewrite this equation here, the Schrödinger equation, just to look even closer to this. We assume that the potential is 0, just for a second, and then we just simplify the h bar here with one of these h bar squares here. We move the I to the other place, and then we end up with an equation like this. And as you see, the two equations just look like pretty much the same. So what is the meaning of this diffusion equation in classical mechanics? So imagine that we have a function like this, okay? So this function may represent the temperature as a function of the position at a given time. And let's assume that the function is higher here at x equals 0, okay? So we take a picture of the temperature of a given system at t equals 0, and we plot the temperature as a function of position. And we can see how there is a warm spot here at the origin. The origin is hotter than the rest of the system. So if we take the question now that we want to solve is how this temperature will evolve with time. So we take this picture at t equals 0, and the question is what would happen with the temperature as a function of time? From the diffusion equation here, we can see how the change of the temperature as a function of time will depend on the curvature of the temperature. Okay, so this second derivative of this function with respect to the position square, remember that is directly related with the curvature, as I explained a few slides ago. So here, just taking a look to this figure, we can see how there are regions between minus infinite and this point here, where we have a positive curvature. So the slope here is positive, but it is getting steeper when we move to the right. So that means that the first derivative is, with respect to the position, is positive, and the second derivative is also positive. That means that we have a positive curvature here. Then we have another region between this line here and the origin, where the slope is positive, but it is decreasing. When we move along the x direction, the slope is decreasing. That means that the slope is positive, but the curvature is negative. When we cross here the origin, we find here another region where the slope is negative, and it is getting steeper when we move to the right. So that means that the slope is negative and the curvature is also negative. And then finally, we have another region here where the slope is negative and it is getting less steps. So that means that we have a slope that is negative, but the curvature is positive, okay? So after this analysis, we can solve in a hand-waving way how the temperature will evolve with time. And in particular, just as the diffusion equation is going to tell us, the temperature will increase in those regions where the curvature is positive. That means that the temperature will increase here in this region, and the temperature will increase also here in this region. And it will decrease in those regions where the curvature is negative. So the temperature will decrease in this central region around the central spot. So that means that the energy from the initially warm regions diffuses into cooler neighboring regions. Okay, so it will make the temperature more homogeneous all around the system. So this is the classical solution of this diffusion equation. And we can wonder whether this will happen also if we replace this classical equation by the Schrödinger equation here. And the answer is, okay, the quantum particles and system will diffuse sometimes, but not always. The most important difference between the classical equation and the quantum equation is the fact that there is a factor of I in the quantum equation, in the Schrödinger equation. So the wave functions may be complex, and this is a very important and essential point of the Schrödinger equation, and they may exhibit oscillatory behaviors rather than diffusing under some circumstances. So this is a very basic difference between quantum mechanics and classical mechanics. But I think just taking a look to this example of the diffusion equation in classical mechanics, you can get a flavor of how the Schrödinger equation will behave. So what is the interpretation of the wave function? So the wave function is the function that solves the Schrödinger equation. So what is the interpretation of that? So I will come back to this later, but the physical interpretation was due to Max Born. It was very close to the publication of the Schrödinger equation almost 100 years ago. And within this interpretation, the module square of a particle's position wave function, and the module square, remember that this object here may be complex. So the module square of a complex number is the conjugate gradient of the complex number times himself. So this module square of the particle's position wave function gives the particle's position probability density function. So how likely it would be to find the particle at that particular point. So in the one-dimensional case that we are discussing here, this will be the probability per unit length. So if we take the integral of this probability density over any spatial interval, this will give us the probability of finding the particle in that region of space. So if a wave function oscillates with time or diffuses, the probabilities distribution will change, okay? So the probability of finding the electron in that particular position will change. So as I was describing before, the wave functions that satisfy the Schrödinger equation appear here under first order time derivative with respect to time. That means that we have to integrate once over time. Every time you integrate, you have a constant of integration, okay? So if we have to integrate once, only one constant of integration is required. So that means that the knowledge of the wave function at just a given instant of time completely specifies the state of this particle at all future times. So this is another difference with respect to classical mechanics, where you have, for instance, the Newton's second law, where you have the force equal mass times acceleration. The acceleration is the second derivative of space with respect to time twice. Then you have to integrate twice, and therefore you need not only the position, but the position and velocity. You need two constants of integration. So here in quantum mechanics, you only need the knowledge of the wave function at some instant in time. Okay, so let's move to the next point in our menu. And the next point in our menu is to explain the time-independent Schrödinger equation in this very simplified one-dimensional case. So here, we are going to one assumption, and the assumption is that we can separate the variables. So remember that we have here this object that is the solution of the Schrödinger equation. It depends, or it may depend on the position and time. So our assumption here is that we can separate the variables. So we can just split this wave function in the product of two functions. One of them will depend only on the position, and the second one will depend only on time, okay? In principle, there is no a priori reason for doing this. However, we are going to be able to do this separation of variables when our potential will not depend explicitly on time. So if our potential varies only over space, then we can use this separation of variables as it is done here. So let's check what is the influence, or what is the consequence, what are the consequences of just splitting our wave function that in principle depends both on space and time in this form here. So we assume this, and then we can insert this into the Schrödinger equation, so in the Schrödinger equation, when we were telling before that here we had the function, the quantum wave function psi, then we can write here this separation of variables, and the same here at the right-hand side of the equation. Then, since this function here, psi, does not depend on time, this can be considered as a constant, so it will jump outside the partial derivative, and the same will happen here with the capital T. Okay, so this capital T will not depend on the position, so it will be considered as a constant, so it can jump outside of the derivative. Okay, so I will end up in an equation like this, with an equation like this, where we can replace also the partial derivative by total derivatives, because now the function here only depends on time, so this will be a total derivative of this capital T with respect to time, and here this psi will depend only on the position, so we can replace the partial derivative by a total derivative here. So we have an equation like this. Okay. So then I have rewritten the equation here. So now the next step that we can do is to divide both the left-hand side and the right-hand side by psi. Okay. So doing this, I'm just writing what will happen here. So if I divide both sides of the equation by the quantum wave function, this psi of x here will cancel with this, and this capital T here will cancel with this, and here this the psi and the T will cancel with this. Okay, and then we end up with something like this. Okay, and this there is a very important thing in this equation. If you take a look, you can see how the left-hand side only depends on time, while the right-hand side only depends on position, on space. Okay, so if this has to hold, then the only way of just for the happening of this is that both the each side of the equation must be a constant. Okay, there are no other ways of making of accomplish with this equation here unless both sides of the equation depends are equal to the same constant. So let's take a look to the left-hand side here. So I have here the left-hand side equal to a constant. Then I can just move the I and the H bar to the other side of the equation. Then I can integrate here over time both the left-hand side and the right-hand side of the equation. And then here on the left-hand side, I will have the natural logarithm of this capital T function. And then for the right-hand side, I will have the constant of integration divided by the imaginary number and H bar. Those are constant that will move out of the integral times time, okay? And then finally, we take the exponential, we take the exponential on both sides of the equation, we end up with an expression like this. And if I call this constant equal to E, I have this final form for the time dependent part of the solution of the Schrödinger equation. Okay, so that's for the time dependent part. So here I am considering what's happening at the left-hand side of the equation. So now we can take a look to what will happen at the right-hand side of the equation. Okay, so for the right-hand side of the equation, I'm writing here the right-hand side, and it has to be equal to the same constant as before. Okay, so this is the same constant as in the time equation. And then we can multiply both sides by the psi x, and we arrive to the time-independent Schrödinger equation, that is written in this way here. Okay, so this is in many cases this is the Schrödinger equation you are used to look at. Okay, remember that this is only the solution of the spatial part. So we have also the time-dependent part that was described in the former slide. So the solutions of this will describe the spatial behavior of the quantum wave function. And then, as you will see here, and you will see here, the solution will depend on the potential in the region of interest. So next week, I will show you how to solve these equations for different potentials here. This potential may be an harmonic potential. In the case of the harmonic oscillator, may be the Coulomb potential generated by a proton in the case of the hydrogen atom, or may be even zero in the case of the most simplified model to simulate a metal, as in the free electron gas. Okay, so next week we are going to check how to solve this equation in particular cases. So this equation here can be considered also an eigenvalue equation. And in particular, if we define here the Hamiltonian operator as the sum of the kinetic energy term plus the potential energy term, then we can just write this time-independent Schrödinger equation in this way here, where we have the Hamiltonian applied to our spatial part of the wave function equal to a constant that will be the eigenvalue times the eigenfunction again. So we can write the time-independent Schrödinger equation in the shape of an eigenvalue equation. So what is the meaning of, in many cases, you will read about stationary states. So you have seen here how the wave function depends both on time and space. And in particular, it changes over time. And it changes over time following the solution that I was describing before. So this is the solution of an exponential, complex exponential function. So if this function is changing with time, so what is the meaning of a stationary state? So a stationary here in this case means that the wave function may be separated into a spatial and a temporal functions, as I was describing before. But the most important thing is that all the quantities, such as the probability density or the expectation values of a given operator, do not vary over time. So that's the meaning of stationary states. So that the expected value or the probability density or whatever thing that you can measure will not change over time. So the question is, how can this be possible? So take, for instance, the case of the probability density. So the probability density to find a particle in a given state, it is related with the modulo square of the wave function. And the modulo square of this wave function is just the product of the conjugate of the wave function times the wave function here. Okay? So we have here, we take the conjugate gradient times the wave function here, and we can check how the part that, or the part that is related with the solution with the temporal function here cancels out. In particular, we have here this exponential with a plus sign here. We have here the exponential with a minus sign here. So they will cancel each other. And at the end of the day, this probability density function will not depend on time. So that's the meaning of a stationary state. Okay. So that's, then let me move to the next step in our menu. And is, okay, we have been working in a very simple case just to set up the notation and just to catch the most important message that is hidden in the Schrödinger equation. So let's move to the next step. And the next step is the generalization to 3 dimensions, okay? So in 3 dimensions, now to specify the coordinates or the position of a given electron, we need a 3-dimensional vector, okay? So we have here in Cartesian coordinates, we have this position here that will have another a given component along y, x, y, and zeta in Cartesian coordinates. That means that we will need to replace the second spatial derivatives that before was only the second a second order partial derivative with respect to x. So this has to be replaced by a Laplacian, okay, by the Laplacian operator, where the Laplacian operator in Cartesian coordinates take this shape here. It's just the sum of the second order partial derivatives with respect to the 3 directions in space. And then, considering this, we can just, we have to, instead, the wave function will not depend just on a given spatial direction, component x, it will depend on 3. So when we write x here, we have to write here the vector r. And when we write here the second order derivative with respect to space twice, we need to replace this by the Laplacian. And that's all, okay? So with this, we have generalized our 1-dimensional Schrödinger equation to the 3-dimensional case. And as before, we can assume that in some cases, we can just make this separation of variables here. So we can just consider that the solutions of our time-independent Schrödinger equation can be written as the product of a function that depends only on positions and another function that depends only on time. And doing this in the same way as before, I will not repeat the reasoning behind, but with this, we will arrive to a solution for the temporal part that is the same as before. So we will have this oscillatory behavior with time. And for the spatial solution, we have this 3-dimensional analogous of the spatial equation to the 1-dimensional case that was described before. And as it happened before, we can write it in the same, under the shape of eigenvalue problem, considering this Hamiltonian here. So I don't know if I have a few extra minutes or whether I should stop here and leave this for next Thursday. So may I continue for just 3 minutes or 4 minutes?
Yes, please, sir.
Okay, so that's just the final issue that I want to discuss here in this lecture is what is the meaning of this electronic wave function and the principles of what is called the Copenhagen interpretation. So Schrödinger proposed his equation in 1926. But then the problem is, what's the meaning of the solutions of my equation? Okay, so Schrödinger gave an interpretation that was wrong. So in particular, what he said was that the wave function of a charged particle may be related to the spatial distribution of some electric charge. So that was the interpretation given by Schrödinger, and this was wrong. So the right interpretation of the solution came after Max Born, that in the physics community, he's well known because he was proposing many different things. So the Born effective charges, the Born-Oppenheimer approximation, the interpretation of the electronic wave function. But something that is unknown for many people is that he may be also known because he was the grandfather of the actress and the singer Olivia Newton-John. Okay. Maybe for the general public, the Grand Doctor is more popular than the Max Born. So what is the interpretation of the wave function? So that's what is called the Born's rule. And as I was describing briefly before, so the wave function represents a probability amplitude. Okay, so how large is the probability of finding the electron in a given space in a space. In particular, it is the magnitude square of this wave function what determines the probability that a certain result will be obtained with an observable is made. So what Max Born was saying was that the modular square of the wave function is the thing that represents the probability amplitude. Okay. So the thing here is that the wave function is not a measurable disturbance in any physical medium. So the wave function can be used to determine the possible results of measurements of quantum observables and to calculate the probabilities of those results. So this is something that was discussed from the very beginning of the birth of quantum mechanics. And it gives rise to what is called the Copenhagen interpretation. So I will not enter into the details of this interpretation or the debate behind the Copenhagen interpretation, and then Einstein and others were proposing some other interpretation. I will not enter in this debate, but I will just enumerate here the most important principles of this interpretation. So I have separated this into different issues. So the first one is the information content, and it says that the quantum state includes all the possible information about a quantum system. So there are no hidden variables with additional information. Then regarding the evolution in time, so the Copenhagen interpretation is telling us that over time, the quantum states evolve smoothly in accordance with the Schrödinger equations unless a measurement is made. So what does happen with a measurement is made? So it's called the wave function collapse. So whenever a measurement of a quantum state is made, the state collapses to an eigenstate of the operator associated with the observable. Okay. So then here we are talking about measurements. So we can wonder about what are the measurement results. So the value that is measured for an observable is the eigenvalue of the eigenstate to which the original quantum state has collapsed. Then there are another very important principle that is called the uncertainty principle for some observable for some properties that are incompatible. That's the case, for instance, of position or momentum or energy and time and others. So this uncertainty principle is telling us that these properties cannot be simultaneously known with arbitrarily great precision. Then we have the Von rule that was described and was mentioning before, that the probability that a quantum state will collapse to a given eigenstate upon measurement is determined by the square of the amount of that eigenstate present in the original state. Then we have the correspondence principle that makes the connection between classical mechanics and quantum mechanics. And this correspondence principle is telling us that in the limit of very large quantum number, then the results of measurements of quantum observables must match the results of classical physics. And then finally, the complementarity principle that says that every quantum system includes complementary wave-like and particle-like aspects. So whether the system behaves like a wave or like a particle when measured is determined by the nature of the measurement. So with this, we are ending essentially what I wanted to describe in this lecture, that in summary, what we have done is just to introduce the Schrödinger equation as the most basic and fundamental equation of nature for the physics that we are going to deal with. The solution for this equation is for a many particle system in interaction is very difficult. We are going to explain how to solve it in the ASESMA school, but here in the PreSchool, the most important thing that I wanted to describe is the meaning of all the terms that appear in the Schrödinger equation, how we can go from the time-dependent Schrödinger equation to the time-independent Schrödinger equation in the case where we have a potential that does not depend on time. And then making this separation of variables, we have the solution for the time, and then we have the solution for the spatial part. Then we have generalized the equation from 1 dimension to 3 dimensions. And finally, I was describing that what is the physical meaning of this of the solutions, in the sense that it is the modular square of the solution that is giving us the probability densities. And finally, I was just enumerating the principles of the Copenhagen interpretation. So with that, I will finish the lecture today. Next week, we are going to resume the explanation from the time-independent Schrödinger equation, and I will solve it in different cases. And then I will devote the third lecture for question and answer. So I don't know if you have any question regarding with today's talk. Hello?
Ezekiel, you raised your hand. Can you unmute and ask?
All right, thank you. Thank you for the lecture. This is an eye-opener. Yeah, so when you were describing the solution of the Schrödinger equation in 1D, so you assumed that the potential is not time dependent. Now, if the potential is time dependent, what will the solution look like?
Okay.
How do we go about this? Yeah.
The point is that what I wanted to, let me check if I can go back. Let's see. Okay, here. So here. So at the time of introducing the time-independent Schrödinger equation, the basic assumption here, it is what we are saying here is that we can split the solution as the product of a part that depends on the space and a part that depends only on time. So then the basic question that you can ask is, okay, can you do that? I mean, can you? It is something that can be done always. So in principle, there are no reason for this function to work like this. But then the thing is that it will always hold if your potential does not depend on time. So if your potential is fixed, this can be done. And if your potential that depends on time, then you have to solve the time-dependent Schrödinger equation. Okay, so you have, and that's one thing that very likely you will follow in the school, in the sense that you will search for the time-dependent density functional theory. What you are going to do is to propagate this solution with time. Okay, and there are different ways you are going to solve this for a particular time t equals 0, and then you are going to propagate and to solve this time-dependent Schrödinger equation, including explicitly the time in the solution. Okay. So does it solve your question? So in the case where you have a time-dependent potential, then you have to solve directly this equation here, just propagating the solution of the Schrödinger equation. And there are different ways of propagating this solution. There are different propagators. And okay, then you have to include explicitly the time-dependent part. So I don't know if there are any other questions. So Timothy, you have has raised his hand.
Yeah, thank you. Yeah, thank you very much, Prof, for the presentation. While you are explaining solving the time-dependent Schrödinger equation, you ended up with a solution of time-independent Schrödinger equation in one dimension. My question is, if it is in 3 dimensions, are we still going to end up with the same answer?
Yeah. So this was included in one of the slides. So you can make the same kind of approach of considering that you can split your solution in a part that is time dependent and another part that is spatial dependent, and then you can do the same. You can play the same game. Okay. So this was included in one of the slides. So let me share the screen again. So this is okay. So this is here. Okay. So in 3 dimensions, you have essentially the same. You can play the same game as before, and then you can end up here with a solution for the temporal part and another solution here for the spatial part. Okay, and this is in 3 dimensions. Take here.
No, the applications.
Sorry. Hello. So I was missing some question or. Hello. Hello, Victor.
Yeah, thank you for the lecture, Prof. I wanted to ask that if one may ask that, is there a fundamental proof to how the Schrödinger equation came about? Is there any fundamental proof to it, or it's just an equation from experimental results?
Well, that's a very important question from the point of view of history. So, at the time where Schrödinger was working on this, so that was the first days of quantum mechanics. So they were starting all of this. They were searching for. So they had the impression that somehow matter should behave like a wave, and they were searching for, let's say, a wave equation for matter. Okay, so they were just taking a look to this. They were trying different things, and at the end, okay, Schrödinger came up with its equation. So answering there are some hints behind this. I think I can complement the slides because, I mean, for just to answer this question, I would need some help from to check, okay, there is this relationship. Let me check here. Let me check if I can share the screen again. So it is this in here. So here you have the relationship between for a wave, you have here the relationship between energy and frequency, or between momentum and the wave number. And then these were known for waves. And then just checking or trying to check whether it was possible to find a wave equation for matter. They were just trying to relate the energy here with with the kinetic energy. The kinetic energy is the square of the momentum divided by twice the mass times the potential. Okay, so here, from this kind of just making the connection between energy and then momentum squared divided by twice the mass times the potential and things like that, you can get a flavor about how this, about what was the origin of the Schrödinger equation. Okay, so that's essentially, that was the hints that Schrödinger and others were looking at 100 years ago. Okay, just checking whether they could write something related with a wave equation for matter. Okay, and relating the equations that were known for waves, so the Maxwell equations and radiation pressure and all these kind of things. So we could relate these equations into equations that particles should hold. Okay. So any other question?
Well, Prof, please, I have a question, sir.
Yep.
Thank you very much for today's lecture. Sir, the other time when you were speaking, you talked about solving a time-dependent Schrödinger equation only when our potential is actually time-dependent. So I want to ask, what are the conditions that make a potential time dependent? And how do we identify such a potential? And possibly if you can give me example of such potential in real life application.
Yeah, imagine, I mean, you need to solve the Schrödinger equation for the electrons, okay, for the electronic subsystem, okay? So this electron subsystem depends on or will interact with the positions of the nuclei, okay? So imagine that you can consider that as in many cases it happens like this, you consider that the nuclei are fixed. That means that the external potential that are felt by the electrons will be constant because the nuclei are fixed in space. Okay? Therefore, the external potential does not depend on time. Imagine that the nuclei are moving and the positions depend on time. Therefore, the external potential will depend on time. Okay, and that will be a difference. So that's one case. Imagine this other situation. Imagine that you have an electromagnetic wave interacting with your system. So this electromagnetic wave, the electric and the magnetic field will depend on time. So that means that the external potential will depend also on time. So that's another case where the where the potential depends on time, and therefore you have to solve the time-dependent Schrödinger equation. Imagine that at some point you are perturbing your system. So you just kick your electronic system in some way. For instance, you put a laser pulse or whatever that is that just perturb your system at a given time. So that's another way of where you have to consider the time-dependent solution. Okay, and after this perturbation, very likely the system has been perturbed, and then it will relax again to whatever situation. So that's another case where the potential will depend on time. Okay.
Thank you very much, sir. Thank you, sir.
Thanks to you. Any other question? Okay, if not, I will just deliver the slides to Omololu and to Nicola Seriani. So then you will have access to the slides, okay? And then see you next Thursday.
Thank you so much, Prof. See you.
Thanks to you. My pleasure.
Thank you, Prof.
Thank you.
Prof,
Thank you so much,
thank you
bro.
for the lecture.
Thank you so much, Prof.